We are solving question number 51 of GATE 2017 chemical engineering paper, and the subject is process control and instrumentation. The question is, the open loop transfer function of a process with a proportional controller of gain Kc is given by GOL is equal to Kc into e raised to minus 2s upon s. Based on the Bode criterion for closed loop stability, the ultimate gain of controller rounded to 2 decimal places is dash. So for the given open loop transfer function, we have to find the ultimate gain of controller using this Bode criterion for closed loop stability. So let's just write the open loop transfer function. Open loop transfer function we have been given as GOL into Kc into e raised to minus of 2s upon 1, and we have been asked to find the ultimate gain, that is Ku, using Bode stability criterion. So according to this Bode stability criterion, we define this ultimate gain as the maximum value of the controller gain that can provide a stable closed loop response. So we define this if the controller gain is Kc, then we can write this Kc as Ku upon Gm, where Ku is the ultimate gain and Gm is the gain margin, and we find this ultimate gain such that this gain margin should be always greater than 1 to ensure stability. So using this Bode stability criterion, we define this ultimate gain as Ku. So that is what we have been asked in this question to find out. So for that, we need to find this value of gain margin. So gain margin, we can define it as the inverse of amplitude ratio at the phase crossover frequency. And that is gain margin is equal to 1 upon amplitude ratio at omega equal to omega C0. So for this, first of all, we need to find this gain crossover frequency. So we can find this gain crossover frequency as the frequency at which the phase lag is minus 180 degree. That is phi overall is equal to minus of 180 degree. So for this given transfer function, we can write the overall phase lag as, for this Kc, it will be simply 0. For e raised to minus of omega tau, it will be simply minus of omega tau, and we need to convert it into degrees, so it will become minus of omega tau into 180 upon pi, and for this 1 upon s, the phase lag will be minus of 90 degree. So we can replace the values and find the value of minus omega. So this will become minus of omega tau is 2 into 180 upon pi is equal to, this will become minus of 90 degree. So we can write this as 360 upon pi into omega is equal to 90 degree. That is omega, we can write it as pi into 90 upon 360, that is pi by 4. So the crossover frequency we found out as pi by 4. Now we need to find the amplitude ratio of this transfer function at this frequency. So amplitude ratio will be simply multiplication of all amplitude ratio of this individual term. So it will be Kc into one. So for this e raised to minus 2s, the amplitude ratio will be 1, and for 1 upon s, it will be simply 1 upon omega. So now we can replace the value of omega. since we have to find the amplitude ratio with crossover frequency as pi by 4, so this will become kc upon pi, that is amplitude ratio will become 4 kc upon pi. So from that we can write the gain margin as 1 upon amplitude ratio, that is gain margin will become pi upon 4 times of kc. Now for this body stability criterion, we know that kc is equal to ku upon gain margin, that is you can write ku is equal to kc to gain margin, and gain margin we found out as, let's just write kc as such, and gain margin we found out as pi upon 4 kc, that is pi upon 4 kc. Kc will get cancelled out, and the ultimate gain we can write it as pi by 4, or numerically we can write it as 0.785. So the final answer, that is based on the Bode criterion for closed loop stability, the ultimate gain of the controller rounded up to 2 decimal places, we can simply write it as 0.78.